Hi, this is Tom Sargent. I'm a teacher in PhD first quarter PhD macro. So I'm in my office. I'm recording this first video. So my job is I've got instructions from the department chairman to and from my colleagues in the macro sequence and in the department to Bellmanize you. Um, to to teach you a set of tools for building a class of models. And what I'm going to begin with, I'm going to go really slowly because I have to, because of my nature. I'm going to start by defining a bunch of terms. Um, and I didn't make these definitions up, just so that we're we're on a common ground. So here goes. I'm going to share my screen, and um, I'm just going to I'm just going to define some terms that are widely used today. Um, hear them all over the place um, in this day of chat GBT and so on. Okay, so here goes. Um, the terms that you hear all over the place are data, um, information. You hear about big data all over the place, and some terms you may or may not hear in the press, but well, we're going to use them all over the place. A random variable, non-technical definition of a random variable we'll talk about. A model, statistic, what a statistic is, as opposed to statistics. What is a statistic? What's a parameter? What's a sufficient statistic? Now you might say I'm disorganized because I put statistic first and then I put parameter, then I put sufficient statistic. Why didn't I put sufficient statistic before parameter? You'll see. And then we're going to have an agent. I'm going to tell you, well, that's what we're going to talk about this whole class. As a matter of fact, that's what economists talk about. So so here goes. Um, so data. Um, so so data is a collection of observations, a collection of measurements. That's what we mean by data. And it comes in kind of two forms. We'll say it comes in two forms. Um, it'll come in the form of discrete, um, and we'll see that in this model, in this class. Discrete means it can take on only a certain number of prescribed values by the nature of what we're measuring. So it could be yes or no. That's discrete. It could be yes, no, or maybe. And that's discrete. There's three things. And then what the data is going to have, we're going to have a collection of observations. If it's discrete, we often organize it into a histogram. And so what's a histogram? It's, well, we write down the possible values that X can take. It can take on values, say, X1, that's a particular value, X2, Xn, where these are particular values. These are particular values. These are the data. Yes, no, maybe, um, and so on. And all we're going to do is we're going to count the number of X's that are equal to I or equal to X of I. So I guess in this notation, it would be the number of points um, where the data are equal to X bar sub I, where those are our measurements. And that's a histogram. That's discrete. The analog for continuous, let's say that X is some continuous uh, variable. I didn't say random variable. It's just some continuous measurement that lies on the real line. It lies in R. Okay. And now all we're going to do is we're going to have this delta function, and it's literally it's a generalized function. Actually, it's a direct delta function. Delta of some s is going to equal 1 if s equal to 0, and it's going to equal 0 otherwise. So if x is equal to xi, we get 1, and we're just gonna count the number. So this is a continuous state analog of a histogram. That's what this is. And then what we're going to do is we can have a CDF version of this, a cumulative histogram. And all that is so we have, by the way, you're going to see I make mistakes all over the place. This should be, fortunately, I can erase. This should be x sub, the number of possibilities. So I'll say this is x sub, I don't call it j, for j is the number of possible values. It's the number of possible values. So those are values that can occur. I here is indexing observations. Okay. So those are our data. That's what data are. A collection of observations that we organize in this way, and these things are called. This is often called the empirical distribution. Sometimes it's called the empirical distribution or measure. You'll hear those words, but that's what the data are, and that's how we organize it. Okay. So now the next thing. So what's a random variable? Well, I'm going to say, well, you could look this up in your probability course. It's a variable that's described by a probability distribution. It's a variable described by a probability. It has a probability distribution. So I want to distinguish. I want to distinguish the random variable from the random variable versus the realization of the random variable. So what is it? What is a probability distribution? And we're going to take there's different people that have different interpretations of probability distributions. The frequentist interpretation is it's a relative frequency. So it's a frequency that would be that you should anticipate if you take a very long sequence of identically independently distributed draws from the probability distribution. And if you take a really big sample and then you form a histogram, the histogram is going to converge to the probability distribution. So I can give you a link to some videos that talk about the senses of probability distribution. So this is the frequentist. It's a relative frequency if you take a large number of draws from the probability distribution. Okay, so this distinction between the random variable, this is an object that's described by a probability distribution, and the realization, that's a particular draw. And something that's going to be a subsidiary, a concept that we're going to use is independently, identically distributed. We're going to use that all over the place. We'll use it later today. And so that's something that you'll be using from the prerequisites that you have for this class. Okay. So what's a model? Or if you could say, my friend Neil Wallace would say, don't call it a model. Okay, call it a statistical model. Statistical model. So what a statistical model is, it's a probability distribution over either a random variable or a vector of random variables. This could be a vector of random variables. And in this class, it will be mostly a vector of random variables, a vector. Indexed by a set of parameters. So theta is a parameter or a set of parameters that pins down a probability distribution. And theta lives in some set of possible parameter values. These are maybe these are possible parameter values. And so a particular model is pinned down by a particular theta. So so here's my definition of probability distribution. A model is a probability distribution indexed by some parameters. A manifold of models is swept out as you vary the parameters over possible values. So you should check out whether an application of this language would think of the univariate normal distribution with mean mu and variance sigma squared. That has two parameters. So I'd write that as f of x conditioned on mu, not conditioned on, indexed by mu and sigma squared. And as I move mu and sigma squared through some space of possible parameters, values, that's an index, that's a manifold of models. So when I say model, a statistical model, that's what I mean. And we'll be imperialistic with this definition because we'll let x be vectors. So if x is a vector, could be indexed by time. Or could stack up, it could be a time series, a whole entire time series, where x is, x could be GDP in year 1, GDP in year 2, GDP in year 3, and stack those all up. And let's say up to t, that's a time series. That's one draw from this probability distribution. Now, something's going to happen now. We're going to ask, if I adopt this interpretation, what does it mean to be IID? You should ask yourself, what does it mean to be IID if that's my interpretation? Well, if you look at the definition of IID, it actually, with this definition, it would allow correlation between IID would be in the entire draw. I would draw IID draw of the entire X. We'll come back to that. So when we say IID, what do we mean by that? That's going to be a theme. And my colleague, Bill, who's I regard him as a co-teacher, not the TA, but his job description is TA. But you'll see we'll be revisiting IID a lot. We might be revisiting this. Okay. So in the sense of probability, we'll be talking about that is anticipated frequencies in large number of samples, a large number of realizations. Okay. So We've talked about random variables. We've talked about a model. We've talked about parameters. Those are things that pin down probability distributions. And now we're going to talk about statistic. Well, a statistic is just a function of the random variable. So it itself is a random variable. The statistic is a random variable. Think about it. Because we're going to draw, it's a function of a random variable. A realization of the statistic is just you take a drawing of the random variable, and a statistic then would be a function of the observed data. That's what if we take a realization, that's what that would be. Okay? That's what a statistic is. Not the subject of statistics, but it's a statistic. Okay. So now we're creeping up on a definition of information. Kind of a casual one. Okay, so information is different from data. They're related, but it's different. Okay. So if you go to a party with a bunch of statisticians or mathematicians or economists, you want to make sure that you use the words properly. So there's this thing called for a probability distribution, there's this beautiful thing called a Fisher-Neyman factorization. That's the giant, you gotta think of them as either the founders or the systematizers of frequentist statistics, R.A. Fisher and Jerzy Neyman. And they did this in the first 40% of the 20th century. So it turns out you can represent this is a representation theorem. It's a representation theorem. Not going to prove it. It turns out what they observed, and they, okay, why did they do this? Why would anyone want to do this? They were trying to, probably if you watch them in a coffee shop, they were trying to distinguish data from information. That's what they were after. That's why they did this. They were proper use of these words. So I've already told you what the data is. It's a set of observations. And then R.A. Fisher and other people's so you know, so they had this vision. This is going to be the vision of a big part of this class. This is like, let's put this over here, okay? The data, I told you what the data are. Here's the data. These are data. It's a collection of data, which we'll summarize, we've summarized them, for example, in an empirical probability distribution, either continuous or discrete. So these are the data. So we have this empirical distribution. And then what you have is theory. You have theory. And these are models. And what those are probability distributions of X, random variables. These are random variables. These X's over here. See, we're could we say we're abusing or recycling notation? These X's over here, these are, there's no random variables over here. They're just data. There's these histograms. Random variables are all about models. So this is all theory. This is in somebody's mind. This is all imaginary. This is imaginary. It's completely artificial. It's in the theorist or the statistician's brain. So we have this model indexed by some parameters. Models. And actually we have a whole set of them because we have a whole set of models where theta lives in this big set of possible models. So it's not anything goes. It's not anything goes, but it's a restricted class of models that are indexed by these parameters. So Fisher-Neyman, they're probably in a coffee shop. They didn't work together. They were alive at the same time. Well, actually, there's long stories about that. They were both characters, had personalities. They were at the same place for a while. But anyway, so you could think of them trying to figure out what's the relationship between these two. What's the relationship between these? And essentially, what they wanted to do is they want to bring them together. Their want, could call it. This is what they want. Their want operator. They want to bring these together to formalize the relationship. And essentially, you've seen this before, presented a lot better than I'm presenting it now. The whole idea of statistics, the subject of statistics, is with a framework like this is find a theta in big theta that I'm just going to say that explains that I'm going to say explains, put in quotes. What do you mean? These are all new words after, or matches. What does this mean? The data. So they're going to where they're going to fit the model to the data. That's what they want to do. Fit the model to the data. So the Fisher-Neyman notion of information is they want to know what the data says, what data says about theta in theta. That's what they're after. So their measure, Fisher came up with a measure of information, which you learn about in econometrics. But this is what information are there in the data about the parameter? So this is info in the data about theta. That's the Fisher classical frequentist notion of information. So, and it's kind of interesting. You'll notice that all of this is, and by the way, machine learning confronts this all over the place. The only thing the data can tell you about is a parameter or a parameter vector. The theorist, the statistician, or the economist have to pick F. So, what our class is about, and actually I would say like your whole study of economics is about, is figuring out how you should pick F. Remember, this part's in your mind. This part over here is all in your mind. Okay? So this is in your mind. This stuff comes from the stuff over here. This stuff comes from your mind. This stuff over here comes from a combination of nature, or the economy kicking out data, and somebody measuring it. There could be measurement error too there. That affect these, that get infect. I could say infect, not infect the empirical distribution. Okay, with that said, so with that said, I'm going to proceed to come back over here, and let's talk about the Fisher-Neyman factorization. That's where we are, the Fisher-Neyman factorization. Okay, so this is the Fisher um, Neyman factorization formula. It says we can always represent. Represent just means write in a different way. We can represent the probability distribution indexed on a model. This is our model. We can index it as a product. You factor in a product of two things. It looks like this: g of t of x and theta. So we replace x with t of x and theta, and this other function called h of x. We can always do that. And actually, if you've had a statistics class and you've seen the exponential class of models, this factorization becomes really beautiful and informative form. I'm not going to go into that now, but you can always do it. Almost always do it. I'll just say that. So then what is this T of X? This T of X is a sufficient statistic or it's a set of sufficient statistics. It's a sufficient statistic. And H of X is an ancillary statistic. So sufficient statistic is all about this factorization. And if you stare at this, what this tells you, if you stare at this and think what it means, copy down the formula and then stare at it, what does it mean? Well, what it says is that the only part of X that's interacting with theta is this, it's not all of X. It's just some features. You could think of features of X. That's what sufficient statistic are, features of the sample that depend on X. So the T of X, those are features that depend on X, on theta. I'm sorry, the distribution of T of X. See the I want to be careful. This is subtle. I'm going to say it carefully. H of X are called ancillary statistics, or they're just sideshows. They're sideshows. T of X contains all the information about theta that is contained in the sample. Not all the information about, not all the information, but all the information about theta. So when you say information, or when a statistician says information, it's about something. Information is always coupled, and the information in the sample is always about theta, and it's that would be contained in a sample. So you've seen this before in statistics class. I'm just emphasizing. But for a univariate normal distribution, the sufficient statistics are, well, the sum of the x's and the sum of the x squared. Here's an ancillary statistic, xi to the p for p not equal to 1 or 2. Any of those other moments, sample moments, they're irrelevant in terms of they the normal distribution tells you things about them, but they don't tell you anything about theta. Okay, so you'll see that's what a statistician means by sufficient statistic, and that's what I'm going to mean. And you'll see papers in economics where they use the word sufficient statistic, but it's not what a statistician means. It's hard to figure out what it means sometimes. Okay. Then the next thing is reparameterization. Is a parameterization of a probability distribution unique? And the answer is no. And often you will find more than one parameterization. So this is a big thing with machine learning. There's a whole field on how to reparameterize cleverly in order to accelerate your ability to learn about the parameters that pin down your model. That's a mouthful. So I've defined all of our terms. So my charge in this class, so I'm going to break this up now. I define my terms, and so when I say them, you know what I'm talking about. Now, my job in this class, I was told to do this, so I obey orders, is to teach about dynamic stochastic models that are used in macroeconomics. So for me, that means in this class, with the above set up, in this class, I'll just put this over here. There's going to be a break here, right here. For me, X is going to be a vector, and it's going to be a vector, and it's going to be a time series. So a model of a time series, that's also called a stochastic process. So for me, a statistical model or statistical model is going to be a parameter distribution over a sequence of random variables indexed by some parameters. So that's what I'm supposed to teach you about, that we're going to be studying, where this is now going to be a sequence. So it's going to be about a time series. And by the way, you could say, well, suppose you have no interest in macro, and you want to do something else, anything, IO, theory, public finance, international. The same language and the same machinery that we're talking about pervades those fields. So dynamic models in IO or international are all about stochastic processes. So this language I'm talking about is pretty universal in economics. Okay. So now what are we actually going to study when we study macroeconomics? We're going to study models with people in them, artificial people. Literally, when we say artificial people, actually machine learning is what we're doing is very parallel to what they do. We could talk about that because AlphaGo is an artificial person that plays the very difficult game of Go better than or at least as well as any human being. It's a very hard thing. So they consciously tried to make a machine. They used many of the techniques in this class. To AlphaGo, you could look that up. So for us, here's an agent. This is going to be a description. This is going to be, by the way, this is a description of AlphaGo. What for me, cut and dried. What's an agent? It's going to be an objective function. It's going to be a constraint set. And it's going to be a decision rule. And this combination of things is going to apply a probability distribution. So we're going to build a model. So here's what we're going to do in this class. We're going to build models of agents, private agents. Most of the time, well, in the whole sequence, the 4-quarter sequence in macro, we're going to have both government agents, monetary policy authorities, all sorts of agents. Mostly I'm going to talk about private agents in this part because I was told to. So every time there's an agent, you should, somebody tells you an agent, you should be able to spot the objective function, constraint set, and the ultimate decision rule. And when we're done, if I build a model of a private agent, at the end of the day, I'm going to have a probability distribution over the agent's decisions. We're going to see that. So the model that we build of people. We're going to build models of people. And when we're done, we're going to get a probability distribution about their behavior. And there might be many such people who, in some sense, look like ex ante, but not ex post. So there's going to be a whole measure or probability distribution of people, artificial people, each of one of which is an agent. The third and fourth quarter of the sequence is going to be all about that. Second quarter too. Those are going to be the fun things. But if you just kind of back out what we're doing, this is what we're doing. Okay, so now here's what's going to happen, and I'm just giving you an example. We're going to have models consisting of agents who have constraint sets that themselves are models. So the agents that we have are going to be describing themselves. When they look at the world, they themselves have models. Their decision, we can't even formulate their decision model of their decision problems unless we impute to them a model. So it took economists a long time, smart economists a long time to sort through and figure out how to do this in a coherent way. And a lot of progress, very clever things were done by very smart people to get us to where we are today. So I'm just going to give, and so my job is going to be in this class to teach you together. Our job together is to learn about the structure of these models and very slowly to go through and study how they're put together. So I'm going to end this my talking with an example, and it's going to be an example that's it's a very hard problem. I'll just tell you. I'll tell you the problem, and it's hard, and I have simplified the problem. I've stripped out it has features of realism, but to make the problem simpler, quote unquote, I've stripped out lots of things. So here's the example. There's an unemployed worker. I'm not going to solve this problem today. I'm just going to pose the problem, and I'm going to ask you to think about it in the next several days. Think about it. And when I mean think about it, I don't want you to look it up in a book. That's not the purpose. I want you to think about the problem. And if you've seen it before, the next part of this isn't going to be as useful as if you hadn't seen it. If you hadn't seen it from afresh, I want you to think about the problem and kind of like as a sympathetic person and ask, what would you do if you were in this agent's shoes? What would you do? And then figure out why you would do it. So here's the deal. You're an unemployed worker. So time's going to go like this. Time's going to go 0, 1, 2, 3, on forever. You're going to start out with unemployed. So you're initially unemployed. So at the end of time -1. So starting out here, you were unemployed. Okay. And now to make it easy, I'm going to assume that you live forever. Unrealistic, you say? Yeah, I'm making this assumption to make the problem easier. So we'll change that later, maybe, if you don't like that. Okay. You live forever. And here's what you care about. What you care about is you care about the following. You care about beta is a discount factor that's constant. It's between 0 and 1. Beta is this discount factor. Okay. between 0 and 1. And what you care about is the present. Okay, this is a mathematical expectation because we're going to have random variables. What you care about is the discounted. We'll leave out the expectation for a minute. It's this is the discounted present value of your income. This is income at time t. And it consists of two parts. If you're employed at a wage W, you get W. And notice there's no T here. I did this to simplify things, and we'll see them. If you're employed, you get W. So think about that. If you're unemployed, you get C, and that's from your unemployment compensation. Okay? And then I'm going to tell you, if you're unemployed, you start out being unemployed. So then each period, you were unemployed the period before, you draw a wage W that's distributed from, I'm going to say a CDF F to work at that wage starting today, forever. So each period you were unemployed, the period before, you draw a wage. And F is a, it's a, it has the property that F of 0 equals 0, and there's some upper bound. There's some upper bound on F of some upper bound. Equals 1. So this F is some function that's some right, some right continuous. So I drew it wrong. It's right continuous. It's increasing. That's W. Here's B. And here's 1. And here's 0. It asymptotes to this. Okay. So each period you were unemployed, you draw from W. The successive draws are IID. And you can take it or leave it. There's no negotiation. And there's no recall. That's what take it or leave it means. You can't go back and get another. You can't get another one. So each period you draw from F, that's what IID means. Okay. And what do you know? So what does the worker know? Okay. So what does the worker know? So put yourself in the shoes of this person. And you can see it's stylized, but it's almost. So the worker knows. In order to say anything, I have to say what the worker knows. I'm going to let the worker knows a lot. The worker knows F. He knows this distribution. He knows C. He knows beta. And he knows, I'll call this equation. He knows this equation star. So he knows the whole structure of the problem. And he knows all of this stuff. He knows the rules. He knows the rules in the timing protocol. That's what he does. So that's what he does. Now, what does he try to maximize? Well, so I want to know what he should do. But first I have to complete this, I have to come back and tell you, here I drew this. I kind of said, let's forget about it now. Here I have this E. It's the mathematical expectation I'm going to say knowing what you know at time minus one of this whole thing. I want to, and so I want to maximize the average value of this uh, over all possible things I could do. So if you could ask, now, if you kind of think about that, it says you could ask, well, what is the probability distribution? So well, I'll say it this way. This is E over the probability distribution of this whole sequence. That's what I mean by that. That's what I mean by that E. That's what I mean by that E. Okay. That's what this is. Okay. And now I've told you everything about the problem. And now I want you to do without looking at a book, because I've looked at the I know the qualifications of the people in this class. They're very smart. Everybody who's in this class is very smart. Okay, so I told you everything. I don't want you to look in a book. I want you to think about this brand new. Even if you saw it before, don't get out your notes. Think about what you should do and think about the problem at this level. Um, I'll just tell you a couple things. That's the problem. So what should the guy do? Now he or she, every period that he's unemployed faces this decision again. Each period that you were unemployed. Once you so here, I could draw a picture, kind of this is me. This is Sergeant kind of starting to think about this. Wait a minute, this problem. I was thinking about this. Here's your, you know, you're unemployed. You start out unemployed, and then you're employed. And then I'm just going to kind of draw a graph. If you're unemployed, you get a wage offer. If you accept a wage offer, you go here, wherever. If you reject the wage offer, you go there, you're unemployed. And if you accept, you get W. If you reject, you get C. But W, that was drawn from F. So if you reject a W today, you get another chance tomorrow, and you get unemployment compensation of C. So what should you do? And if you start thinking about this, well, maximize the expected value. But the expected value over a probability distribution, you are choosing the probability distribution of the YT sequence. Why do I say that? Look at this graph. So do you know the probability distribution? Well, after you figured out what you want to do, you know it. But part of the problem is you have to figure out the probability distribution of Y. Okay, so that's the problem. And I ask you to think about it. And I'll tell you some people who thought about problems that were actually, in some sense, a version of this problem, but easier, and who could not solve it. Well, one is Milton Friedman. The other is George Stigler, and a bunch of lesser people. So some of the smartest people in the 20th century couldn't solve this problem. Then they thought about it. They thought hard about it. So I want you, and the reason I put this on the table is to, well, we're going to be solving problems like this in our class and other ones. So we're going to be studying tools that, no offense, but few of us are as smart as these two people. They couldn't solve it. We're going to be able to solve it, even though we're not as smart. And the reason is we're going to have the tools that we're going to be studying. So that's enough for now. We're going to have a lot of fun.